It's springtime for Butser at Trinity. Okay, so what we've got here is problem number 20.1 from Unit 6. We're not just looking at forces, we're looking at spring forces using Hooke's law. And what we have in this problem is a 10 kilogram mass placed on a frictionless horizontal surface. It's connected to a spring that has a spring constant of 339 newtons per meter. And when the spring's released, the mass has an initial positive acceleration of 10.2 meters per second squared. So what's the displacement of the spring as measured from the equilibrium before the block was released? And we got to be careful about the sign of our answer here. So let's see. We have a spring here that's been compressed by some amount, and there's a block at the end of it. And this block's got a 10 kilogram mass. Now we know when we release this compressed spring, this block is going to accelerate out with a positive 10.2 meters per second squared. So what we're already saying is that the right is positive and the left is negative. Okay, this means that our displacement of the spring will be a negative value because we displaced the spring to the left. We compressed it in. Okay, so because this spring was compressed to the left, it will have a negative value of x. Now, if we think about this, what forces are acting on this block then? Well, the only force acting here is a spring force to push this out. So if we set up Newton's second law, the sum of the forces equals a mass times acceleration, the only force we have is a spring force, and it equals the mass, which was 10 kilograms, times the acceleration, which is a positive 10.2 meters per second squared. So we could quickly say that 10 times 10.2 will be 102, and that is the spring force. But that's not what we want. We want the compression distance, and that means we need to use Hooke's law here. We know with Hooke's law, a spring force is equal to negative kx, where k is the spring constant, a property of the spring itself, how it was built, its thickness, the number of coils, the material, multiplied by some elongation or compression factor, so some distance here, and that will equal some amount of force, the 102. In our case here, we know what k is. We know k is 339 newtons per meter. X equals 102 newtons. And if we simply divide each side by the 339, the newtons will divide out, the meters will become our unit, and technically speaking, if we want this in terms of x, we should divide by the negative as well. So let's put the negative over there. So we're going to find that x is going to equal negative whatever 102 divided by 339 is. That is 0.3. So 0.3, I guess, yeah, 0.3 meters for that value. Meters. Okay? We know it's negative because it has been compressed into the negative direction because we said the right direction was positive. And we just set up a quick little F equals ma there and recognized Hooke's law, gave us our answer. Okay? Remember, this negative in Hooke's law always represents that it's a restoring force. It's always going to try to go back to an equilibrium position. Because if this spring was just at rest, the block would be out here, and the spring wouldn't be compressed or stretched at all. It would just be sitting. If we stretch the spring out this way, it wants to pull back. If we compress the spring like we saw, it wants to push forward. So that's all the negative means. It means it's just doing the opposite for the force of whatever direction you pulled it in. So since we pulled it in the negative direction, we compressed it, it wants to push in the positive direction. And that's it. So nothing too fancy of a problem here, just more F equals ma with a little bit of Hooke's law, and that gave us our answer. So for now, this problem is finished. Adios. Take it easy. Da-da-da.